Good morning. So, are there any questions about anything before we get into today's material? No questions at all? All right. Well, we were looking yesterday at the switch statement and how it gets implemented on the computer, and we had looked at some jump tables for the 32-bit implementation, and now we're looking at the jump tables for the 64-bit implementations. The only difference, of course, is that the addresses that sit in the jump table are going to be twice as big in the 64-bit implementation. There'll be 8 bytes per address rather than 4. So you see this definition of quad word, that's 8 bytes, and then the alignment is 8 instead of 4. But other than that, it's the same conceptually. You just have the addresses laying there for where the blocks of code live in memory, and you subscript into the table, pick up the address, and jump to the appropriate block of code to implement the cases of the switch statement. So conceptually, just the same thing. And then we see that the code, would have this test to see if it's above the 6 is the highest one we had. And so there was a compare, and then you do the jump to the default case if it's out of the range, right? And if it's not out of the range, then you'd go into the table, which is at some address L7, they're saying, and then you for the 32-bit, it would be a 4 here, right? For the 64-bit one, that would have to be an 8 because you're going to take 8 times the index, jump over each individual element is 8 big, right? So then the machine language looks like this stuff, and then the assembly language mnemonics, and then they're just saying, here's the address where that thing at the end of the switch statement lives, and then here's the instruction. So if we went into GDB, which you all are wizards at now, and we ran GDB on a little switch example code, we could do things like if we knew the address where the jump table lived happened to be this address, then we could do something like examine 7 hexadecimal words, and it would dump out the contents of that jump table, and we could see these addresses sitting in there for where the blocks of code live that represent each of the branches of the case statement. But you got to find where the table lives first, right? So it might be slightly tricky. So here's a picture of a bunch of addresses, contiguous addresses in memory, and the value that's stored at those addresses is the address of the blocks of code, right? So that's what the idea of a jump table is. And if you look at the assembly language, here's a bunch of addresses, here's the contents of the addresses, here's the disassembly, the assembly language mnemonics for these opcodes that are over here. And each one is a little, the red one is showing you that's the beginning of one of the blocks of code for the branches of the switch. And you'll see these jumps down to this location here, the beginning of address of our function plus 43 is what that's representing. So it's going down to the location right here, which is after the switch statement is over, right? Each one of them is leaving the result in the EAX register This is how we pass the value back from the function, right? So any questions about this concept of a jump table? Have, we have blocks of code. The addresses are pointed to by the jump table. So we're just using the index into the jump table to go to the appropriate block of code to implement the branches of the switch statement. Questions about how a switch statement gets implemented on the computer? Okay. So we've looked at a bunch of control structures now. We've looked at if then else, do while, whiles, for statements, switch statements, and seen how all of these control constructs that we have in the high level language get mapped onto the architecture of the computer. So any questions about how any of those things, when the compiler sees these in your source program, how it implements it on the computer? If not, we'll go on. The next topic is we want to look in a little more detail at the IA32C calling conventions for the Intel architecture. Remember, there's a different set of calling conventions for the 32-bit machine and the 64-bit machine. So we'll worry about the 64-bit machine separately, but want to look in detail now at how the calling conventions create or implement the semantics, the meaning of what we think of in a high level language as making a function call, right? So the key to understanding this, of course, is that we use a runtime stack. And the way the stack works on the Intel computer is it goes from high addresses to low addresses as it grows. It shrinks, it goes back toward high addresses. Some other computers do it the opposite way, grows in toward high addresses as it gets bigger. Intel grows from the high addresses toward the low addresses. So the stack pointer, this special register we have that just points into memory to where the top of the stack is. When you do a pop operation, it would take what's at the top of the stack, pop it off there, right? And then it would, I mean, when you do a push, I got this backwards. When you do a push, it would put the new value at the top of the stack, and then it would decrement the stack pointer because it grows from high addresses to low addresses, right? So pushing is stick something on the stack and then drop the stack pointer down the appropriate number of bytes based on the size of whatever it was you pushed on there. So if I pushed an integer, then it would do the 4. If I pushed an address on the 32-bit machine, it would go down by 4, right? So that's a push. The pop is just the opposite. It pulls the thing off the top stack and then increments the stack pointer back toward higher memory because it grows from high to low, right? So that you can think of the push and the pop as really just sort of a combination instruction that fetches something out of memory pointed to by the stack pointer and then does an addition or a subtraction to the stack pointer. So it's kind of like a, you know, inside the computer built out of those two component capabilities, but it's something we want to do all the time. So we just have it as one opcode that does all that, does both those things, right? So ultimately, to call a function, a procedure, you use the call instruction, right? The call instruction is also sort of a combination, if you will. It's like a jump that's going to jump to an address that you give it. But in addition, it's going to push onto the stack the address of the next instruction in memory after the call instruction. So we have to have some way to get back to return to where we were called from, right? And we can call the same function from 50 different places in the program. So how do we get back to where we were called from? Well, the call instruction pushes the next address after the call instruction onto the stack. So when we do the return, it's going to pop that off the stack and jump to that location. So they fit together, right? The call pushes the return address and then branches over to the code that represents the function we want to execute, right? The code is living at this address. And then the return is going to pop that return address off the stack and jump back to that location. So if we look at the registers on the computer and what's going on, we have our stack pointer and then the instruction pointer. The instruction pointer always points at the address of the next instruction to be executed. Where in memory is the next instruction to be executed? So we look at this example, and if suppose the stack looked like the thing on the left here, the blue thing, and the stack pointer was pointing at this location 108 was, the 108 has got this 123 sitting in it. And our instruction pointer is pointing at this location, which is this code laying in memory. And the mnemonic for it would be call this address, right? So when the call happens, the following takes place. It pushes the return address, which is the address of the instruction following the call instruction, onto the stack. So you see the return address shows up here on the stack. And since we did a push, the stack pointer went down by 4 bytes, 32-bit computer, 4-byte address, right? So the ESP now contains 104, and the instruction pointer contains the value that we are going to branch to in the call. So really what the call amounts to is push the return address, the address of the next instruction, and then take the argument to the call and load it into the instruction pointer. That's what it does, right? Does everybody understand that? Questions? So now we look at doing return, which is opcode C3, right? And here we are in the function, and we want to do the return. So the stack pointer is pointing right here. It pops the return address off, right, and puts it in to the instruction pointer. That's how we get back to execute the instruction after the call. And the stack pointer, of course, would get incremented in the Intel processor up to a higher memory location. So it's effectively been popped off the stack, right? In reality, it's still laying there. We just moved the pointer up, right? So you see how the push and the pop manipulate the stack pointer and the instruction pointer to create what we think of as jumping over to some subroutine and returning back from the subroutine, right? Well, there's other baggage that's associated with our conception of what a function call looks like in a high level language. We have a concept that, well, the function can have these local variables that supposedly spring to life, come into existence when you call the function. And then when the function's running, it can manipulate those local variables. And then when we return from the function, they're supposed to magically somehow sort of disappear and go away. Well, a stack is the way we implement that, the same stack that we're using to set up the return address from the call and get it back. We allocate space on the stack to hold those local variables. And we'll look at that in more detail in just a second. But the reason a stack works, right, is because of the sequence that things are called is always the opposite of how you return and peel them back off, right? So this is trying to illustrate that we had a function called u who called the function who. You see the call chain over here, u calls who. Well, inside of who, we have a call to am I, so there's that. And then we have another, when we called am I recursively calls itself. So we have another call to am I, and then maybe it recursively calls itself again. And then it starts returning back from the calls. And these would return all the way up to here. And then we're back at who, and then who would have the second call to am I. So you get this, what we call a call tree or the call chain that shows the sequence of things being invoked and then returning from them. And it always peels back in the opposite order of how they got invoked, which is why a stack will work to establish the context of the local variables for a function. So if we have a caller, all right, his base pointer would be pointing up at the top of the white area here, and the stack pointer would be pointing down at the bottom. So that distance between the base pointer and the stack pointer defines what we call the activation record for that function. And when we call a new function, we have the base pointer pointing at the top of his frame or activation record, and the stack pointer pointing at the bottom. That's what all that stuff that we've been seeing at the beginning of these functions where we push the BP and move the ESP to the BP and all that is all about. It's about setting up this frame, but doing it in such a way that we can restore when we return back to the values it had before the call, right? So here's an example of what's going on. We have u calls who. Here's u, right? And when he calls who, we get a new activation record, a frame for the currently executing function who. And the distance between the BP and the ESP is the memory where the local variables for that function can live, right? That's how they spring to life. And when we retract it, that's how they magically disappear when the function returns, right? So then to carry out the sequence, who calls am I, there's an activation record for am I. And then am I recursively calls itself again. And you notice that this scheme that we're using of creating an activation record or a frame for the currently executing procedure sort of gives us recursion for free, right? The same scheme will work because we get a new copy of the local variables, a new set of local variables every time we recursively call ourselves, right? So then we start returning, and these things are getting popped off the stack, and we're restoring the values of the EBP and the ESP are getting back to what they were in the caller at each step, right? So it's peeling these things off. Back to who. Now who calls am I, right? Return from that. Return from who. So what it looks like in more detail is the caller is this area at the top. That's his activation record. And when he wants to call somebody else, he sticks the parameters, the arguments to the function call down at the bottom of his activation record. And then when he does the call, the side effect of the call is to dump the return address on there. When we land in the code for the guy being called, you notice that what we did was we saved off the base pointer, which is the value of the base pointer that the caller wants to have when we get back to him. So we'll restore that to recreate his activation frame when we do the return, right? So we saved it off, and then we took the current value after we saved it off, this little line right here, that address, and saved that in the BP. So now the BP points at the top of our activation frame. And if we needed space to hold local variables or an area for staging parameters to call somebody out of our function, we drop the stack pointer down an appropriate amount of space to create the activation frame of the appropriate size that holds those local variables. There may also be a need for space to save some registers, as we'll see in a second when we deal with the call E save register conventions. We've kind of seen a little bit of that already. There may also be area in here for what are called compiler temporaries. If you have some big nasty expression, the code that the compiler emits may build it up in pieces, right? And so you need these temporary variables that you didn't declare in your program that the compiler really is kind of creating, right? So the compiler temporaries, as well as the local variables that you declared, would also need space to live in your activation frame. So to look at this in detail, we have our function here who has these two global variables, course1, course2, and we want to call the swap function. So this function is named call swap, and he calls the swap function and passes it the address of those two variables that we want to swap the contents of, right? So swap, what's it doing? Well, it's showing you over here that, well, if you subtracted 8 from the stack pointer and moved it down, you would leave yourself some room to put these two parameters in the parameter staging area at the bottom of your activation frame. Now, in reality, it doesn't quite work like that. It doesn't just before it stages the parameters move the stack pointer down. The compiler figures out how big the activation frame needs to be, and up at the beginning of the code for the procedure, in one fell swoop, it drops the thing down to have room for everything it needs. So it doesn't do this little piecemeal thing right before it stages the parameters, but conceptually it's the same sort of thing, right? The parameters get stuffed in there at the bottom of the caller's activation record, and then we do the call, which has the side effect of dumping the return address on there, right? So then we're going to land in this code over here for the swap guy. And what does the code for the swap guy do? Well, here it is. You push the base pointer to save it. See, it has the value that the caller had, what he wants to have for the base pointer, pointing at the top of his activation frame. And so we're saving that off so we can restore it. So when we return back to him, his thing looks like he wants it, right? So we're saving off the base pointer, and then we're taking the stack pointer after doing that push, which modified the stack pointer, right? Saving that into the base pointer. Then when we access the parameters, right, reach back up the stack, we go 8 back to get the first parameter and 12 back, going to higher addresses up the stack, right, into the caller's parameter staging area down there at the bottom of his frame, pulling these parameters out, right? Makes sense? Now, the reason the push of the BP, the BX happens is that the BX register happens to be what we call a call E save register. We'll see in a minute that we basically kind of cut the registers in half and make half of them caller saves and half of them call E saves. So we'll talk about that in just a second in more detail. But we're saving off the BX because we want to use it here. And the BX is what's called a call E save register, which means the caller expects the value that was in it to survive across the call. So to make that happen, we save it and then we restore it because we're going to use it, clobber its value or whatever. So when we get back to the caller, he expects this to have the same thing in it had when he called us. It's a call E save, right? So that's why that's being saved and popped here. But we saved off the stack pointer into the base pointer before we did that, which modified the stack pointer, right? So that these offsets are the proper ones from that point of where the stack pointer was pointing. So here's our pictures of this. The caller puts the two addresses on the stack, does the call, the return address gets dumped in there. Now we're down in the code for the swap function. It pushes the base pointer. That's this value that the caller had in the base pointer gets saved off so we can restore it before we return to him. It needs to point back to where he thinks it should point at the top of his activation frame, right? And then we push the BP, which is sort of irrelevant to the call sequence. But so here's saying that we take the stack pointer and dumped it into the base pointer. Now the base pointer is pointing right here at the bottom of the stack, or the top of the stack, I guess you would call it. And that's defining the top of our activation frame. The distance between the base pointer and where the stack pointer is going to be moved is the place to hold our local variables and things we may need to pass into the function if we call somebody. So you see how this works, right? By saving off the caller's value of the base pointer and then putting the ESP into the base pointer to define our activation frame, right? So when we have the ESP, when we do that push of the BX, the ESP actually drops down, but we've already saved off the value of the ESP at this point into the base pointer, so we can use it to reach back up and get those parameters, right? This is the old BP, the one that is the top of the caller's activation frame. So going 4 back from the value we saved into the BP would get us to the return address that got stuffed on the stack. Going 8 back, since it's a 32-bit computer, that's a 4-byte address. Going 8 back would get us to the first parameter in the parameter staging area. Going 12 back would get us to the second parameter in the parameter staging area, right? See how that works? This is the stuff the caller dumped on the stack before he did the call. And now we can reach back up and get it. And we know it's always going to be 8 back, right? Because we are jumping over the saved base pointer and the return address to get to where it lives. And the reason the second one is 12 back is because they were 4-byte addresses in this case. If they'd been bigger things, then the thing would be at some place further back, right? So that's this business here, getting the parameters out of the parameter staging area, right? And so now when we want to finish our swap function, to return the value of the function, we leave it in the EAX register. That's where the caller expects to see the result saved, is in the EAX register. And so if we do the pops, right, pop BX that we saved, pop the BP, now the BP is restored to what it was when the caller called us. So it's back to what he wants it to have. And the stack pointer is now, after those 2 pops, sitting right here below the return address. So when we do the return instruction, it pops that off, jumps to that location, and now the stack pointer is pointing right back here, exactly where it was pointing before the call happened. So we're back executing in the caller, with his BP pointing where he wants it, and the ESP pointing. This is a bad drawing. It's actually pointing right here underneath that XP. It's that address right there, right? So you see how this fits together to create the semantics or to implement the semantics of what we think of as a function call, having space for local variables come into existence, go out of existence by moving the stack pointer back. So here's the code laying in memory at these addresses and showing you what goes on. And so this is moving the two parameters to the parameter staging area at the bottom of his activation record and then doing the call, right? And then you return to this address, call, dump this address here onto the stack so that when the return happened, you would come back to this address. Does that make sense? How the IA32 calling conventions work? Right? So that we need to examine this caller callee save register business in a little more detail. If we had some code that looked like this in U, and he moved this 15213 into the EDX register, and then he called who, and then who did some stuff and clobbered the EDX register, right? Then when we got back from the call, if the caller tried to add some stuff to the EDX register thinking it has the same value in it it had before he did the call, that wouldn't work, right? Because the callee has clobbered that register. So we need to coordinate between callers and callees which registers the callee is free to clobber, that is, ones the caller doesn't expect to survive across the call, and which registers the callee can't clobber without saving them and then restoring them to the value that the caller had in them because the caller expects them to survive across the call. So this is the concept of a caller save register, is one that the caller does not expect to survive across the call. The callee is free to clobber it. And so if the caller wants it to survive, it's his lookout to save it off on the stack before the call and then restore it after the call because the callee is free to clobber it. The callee saves are that the caller expects to survive across the call. And if the callee wants to use that register, he needs to save it on the stack and then restore it before he returns so that it has the value that the caller expects to survive across the call. So we're just going to cut them in half, roughly. Yeah, cut them in half. We got 8, and these 2 are special, the ESP and the EBP. So we cut them in half, and we make half of them callee save registers and half of them caller save registers. So you just have to memorize which ones are which. Now, it makes sense that EAX would be a caller save, right? Because that's the register that the function return value is put into, right? So it's going to get clobbered by the callee. So if the caller has something in that he wants to survive across the call, he needs to save it off before he makes the call, right? So the A, C, and D, right? Which you can remember, right? ACDC, ACDC. Those are the 3, right? The A, the C, and the D. AC current, direct current. Those are the 3 caller saves. The callee saves are the other ones, the B and the SIDI. Does that make sense? So we've looked at the IA32 calling conventions. The calling conventions for the 64-bit computer are different. We have a different set of conventions we use for that. So rather than just looking at it, let's do it on the computer. On the other one. Okay. So here we are on Schofield, and I've got this sample file here called call32.c. So there's the source code for the program. It's just a little function that has 6 parameters, and it returns the sum of those functions as the integer that it returns. So we declare this sum variable in the main program that's going to call it, and then we call it, we pass it these constants, and he sums those up and hands us the result back, and we print it out. So if we run it, we see this exciting result that the sum of the numbers from 1 to 6 is 21. But what we really want to do is we want to look at the code for the assembly language that comes out of the compiler that implements this to investigate the calling sequence. And the way you would do that is, this is a 64-bit computer. So if I compile something, he's going to compile it for a 64-bit computer. But I can make him compile it as if it was compiling for a 32-bit computer by putting this -M32 in there and say, I want you to compile this C program, but I want you to compile it for the 32-bit computer. And that's what we did. And the other thing we could do is we could tell him, well, I really don't care about the executable, but I would like you to save off the assembly language when you compile this. So I give it that capital S parameter, and then he's going to create this call32.s file, which contains the assembly language for what he created when he compiled this. So that file is this guy. So this is the result that comes out of the compiler of all the assembly language. And there's some stuff in here that I'm just going to tell you to ignore for right now, that we don't really want to worry about. What we want to look at is how the calling conventions shake out and see it actually working in the code on the computer. So any of these little things with a dot in front of them, for right now, just totally ignore that. We'll worry about what those mean later. But here's the label fun1. Well, that corresponds to the function 1 that we had in our C program. And this is saying, here's the code for the body of that function 1. And then down here, here's the label main, and this is the code for the main program. And what we want to focus in on is right here. See all these things being pushed, right? All this stuff getting pushed onto the stack. Well, those are those parameters, right, that are getting pushed into the parameter staging area at the bottom of the main function's activation record. So we were setting up the parameters, and then there's the call to function 1, right? So when we get to function 1, what happens? It pushes the base pointer, right? Saves off the value the base pointer had pointing at the top of main's activation frame, moves the stack pointer into the base pointer to establish the top of our activation frame, right? Ignore all this junk. And then you see what? move 8 back up the stack off the value of where the EBP is pointing, put it in here, go 12 back and put it in there, and then add those two things together. Then it's going 16 back to get the third parameter and adding it to this total that it's accumulating in EAX. Then it goes 20 back, right? Which is the fourth parameter. They're all 4 big because they're integers, right? And accumulating that into the EAX. Then it goes 24 back to get the sixth parameter, the fifth parameter, 1, 2, 3, 4, 5, the fifth parameter. And then it goes 28 back to get the sixth parameter. So it's just summing all those things up like you saw the code doing in the C program. The result is sitting in the EAX register, which is how we return the value back from the function. So now I pop the base pointer to make it point at the caller's top of his activation frame. And when I do that pop, the stack pointer is now sitting right underneath that saved return address. So when I do the return, it pops the return address off the stack and goes back to the location after the call in the main, right? To this location right here. And we got a bunch of stuff setting up the call to the printf function, right? So we go back to our C code. And we see the C code, this is all those pushes. We're putting those parameters onto the stack. Then we did the call of the function, right? And then when we got here, we saw him reaching back up. He saved the base pointer, put the stack pointer in the base pointer, and then he's reaching back up off where the base pointer points to get these parameters at those offsets back up the stack in the parameter staging area of the caller to get them 8 back, 12 back, 16 back, 20, 24, 28 to get those parameters. And you saw him adding the stuff up in the code, and he left the result in the EAX register, which is how you return something from the function, is you leave it in the EAX register. So when we get back to the guy who called us, that is going to get saved. The EAX register is going to get saved into his sum variable that he has there, right? And then we're basically setting up a pointer to a string and the address of that variable as the parameters to pass to the printf function. So we go back over there and we look at the stuff that happens when we get back from the call to the function one. See if I can find it. My eyes are going crossed here. Yeah, there's the call to function one, right? So the result at that point is sitting in the EAX register. And so there you see him saving it off. And that's where the local variable sum happens to live. You'll notice that references to the local variables within my activation frame are negative offsets from the base pointer because the base pointer points at the top of my activation frame. And in the Intel computer, the stack grows from high addresses to low addresses. The offsets to get to the parameters being passed into me are positive offsets going back up the stack, right? So that's taking the result of the function call, right, and putting it in there. Don't worry about the other stuff. So then we're setting up the parameters to the call to the printf function by loading the address of that string and the EAX variable, the address of the address of the sum variable, right, which got put in here, right? So anyways, don't worry about all the dot thises and that's. We'll explain that later, what all that stuff is about. But it doesn't really have anything to do with the actual mechanism that we're using to set up the call, get the parameters, do the return, all that kind of good stuff. So any questions about the Intel 32-bit calling conventions and how they implement the concept that we have in our mind of a high-level language function call? Just pass some parameters, have local variables spring to life, get the return back from the function, have the local variables magically disappear, somehow land back in the instruction after the call instruction, all of that stuff, right? That's how it gets implemented on the computer. You have no questions at all about that? Anything at all? It's all perfectly clear. So then we'll look at the 64-bit calling conventions and look at the code that would come out if we compile this same program for a 64-bit computer, not a 32-bit computer. So office hours are at 2 today. And I have a faculty meeting at 1. So if I'm a couple of minutes late, that's probably why, but I will be there. And we'll answer any questions you might have about your labs or your homeworks or your projects, right? So everybody's reading in the book, in chapter 3 up through these where we're at in the lectures, keeping pace in the book, going through the sample problems that they work in the book for you. That's really crucial that you understand what they're doing in those sample problems as you read the chapter, because the homework problems are just very similar to those ones they've worked for you. And the problems on the exams are exactly the same kind of theme style as those problems, those sample problems that they're working in the chapter. So it's crucial that as you read it, you work through those sample problems they have worked out for you and make sure you understand how to solve those problems, because then you'll be able to do the homework and you'll be able to solve similar problems on the exams. So spend time studying those sample problems that they put in the book for you. So let's see how we're doing on our scoreboard over here. See what it currently looks like. It's like far too many people are leaving things for the last minute. Human nature. So any last questions before we wrap it up for today? See you at 2, or I'll see you tomorrow in class. Have a good one. Bye-bye.